All right, hi honors, and welcome to your honors lecture on enthalpy of formation calculations. I have previously introduced enthalpy, and I am recording this video a little bit early, but I did write the definition that it is the potential energy that may be released or absorbed as heat in a system. And for us, the systems that we analyze are usually chemical processes such as chemical reactions. And then, of course, there are some physical processes such as phase changes that we'll also look at too. But in lecture, I believe I introduced this very generic equation for enthalpy, determining enthalpy based on potential energy diagrams. Okay. As the enthalpy of the product value or the potential energy, I should really say the potential energy of the products minus the potential energy of the reactants is equal to our overall enthalpy of the reaction, right? That's kind of what I introduced in class. Now, again, I'm filming this a little bit early, so maybe it looks slightly different, but overall same concept, right? But you guys are going to learn about, well, how do we calculate the actual enthalpy for a reaction where we actually consider the various products we make, like the various compounds that make up the products in a process. So what you need to know is that we actually have a specific type of enthalpy that we get from a tabularized data for enthalpy, known as enthalpy of formation. Remember that enthalpy is what we call an extensive property, right? Don't forget that enthalpy is an extensive property, which means it depends on the amount of substance present. So we often report our enthalpy values, okay, in what we call enthalpy of formation values. And there's a specific type of notation that we use that differs from how I introduced it in class, which is a very generic, very much off the graph based conceptual understanding of enthalpy. But you guys are getting more of the numerical exact understanding. So enthalpy of formation is a very specific nuanced value of enthalpy that tells us the heat of a reaction for a chemical process. Oh, goodness gracious. For a chemical process / change. Okay. Involving the formation of specific compound or compounds, right? If you have more than one, from their elements in standard state conditions. So that's what the enthalpy of formation tells us, is it actually tells us the heat of a reaction for a chemical process and change based on or involving the formation of specific compounds from their elements in standard state conditions. So what it's kind of saying here is that instead of just doing the sum old, oh, products minus reactants, easy peasy, now we're looking at, okay, well, what amount of enthalpy does each compound contribute to the overall sum enthalpy of the process? So maybe I shouldn't say the word involving. Maybe I should say the word, okay, heat of a reaction for a chemical process or change based on, maybe that's what we should change it to, based on the formation of specific compounds from their elements in standard state conditions. Okay, so now that we kind of understand this breakdown of, we're looking now at the individual enthalpy contributions that each compound in a process contributes to the process to form the overall net enthalpy, the overall net heat flow. We need to look deeper into this idea of enthalpy based on the energy it took to form a compound from their elements. They're, simple elements, kind of like the synthesis reaction. It's basically enthalpy of synthesis of these compounds in standard state conditions. So standard state conditions are defined as the state or phase of elements that exist under conditions conventionally, totally conventionally determined, conventionally determined as 25 degrees Celsius pressure of 1 atmosphere. And if you're dealing with liquids, solutions of 1 molarity, of 1 moles per liter concentration. Okay, and it's under these standard states that we measure the heat of formation for each compound, that we determine each individual's compound's enthalpy that it contributes based on their synthesis. So here's like kind of another way is like, what is the enthalpy of each compound's synthesis? And that's what we're kind of basing our overall enthalpy for a reaction, okay? So here we have a table of measured under standard state conditions. These are all enthalpies of formation for specific compounds, enthalpies essentially of synthesis of these compounds from their most basic elements at the conditions of 25 degrees Celsius. If it's a gas, pressure of 1 atm, and if it's a liquid, a concentration of 1 molarity. And these are the enthalpy or heat values registered for the formation of each, that we will then use a summation, algebraic summation process to determine, well, if it's part of this reaction, how do we know then the overall reaction's enthalpy? So what does this look like using this tabular data? Okay, well, it looks like putting it into equation known as the overall enthalpy of a reaction equation based on standard state enthalpy of formation individual values. And that looks like that we say that the enthalpy of the entire reaction under standard state conditions is equal to the sum, okay, that's the Greek symbol for sum, of the enthalpies of formation of the products times their respective mole value times however many molecules we have of that, minus the sum of the enthalpies of formation of the reactants times their respective mole values, where N is the mole value or the molar ratios. Okay. And so what you're seeing is like, wait, this is super similar to how we set it up on the graph. You're totally right. It's still the same principle. Products minus reactants, except now we're using much more exact numbers and we're considering the various individual compounds that contribute to the process of the reaction, not just this like overall slap product minus reactants. Now we're looking at, okay, in each compound that's a product, how does that contribute to my enthalpy of the process? And each compound of the reactant, how much does that contribute to the overall enthalpy of my process? So let's go ahead and do a practice problem. And then the rest of the practice problems will be in page 4 in your workbook. But we're told, okay, given the following heat of formation values, these specific enthalpy values under standard state conditions that go with synthesizing or creating or forming individual compounds involved in a reaction, is the following. We have a heat of formation value of forming SO2, sulfur dioxide gas, is negative. It's an exothermic process per mole, 296.8 kilojoules per mole. Then we have the enthalpy of formation value for sulfur trioxide is again another synthesis that is exothermic with a value of -396 kilojoules per mole. What is the enthalpy change for the following reaction? Okay, and then of course they didn't give us O2, but here's a little trick. Okay, I'll explain in a second why they didn't need to give us O2. It's because maybe I'll write it up here in the notes. Any pure elements, enthalpy of formation, synthesis, is equal to 0. So an example would be diatomic elements always have an enthalpy value of 0. To form them, it takes essentially no net energy movement. Same thing with pure metals, where you just have like calcium solid or lithium solid or something like that, where you just have a straight metal that's not bonded to anything and it's not carrying a charge, it's just neutral metal. That also has an enthalpy formation of 0. It's just under standard state conditions, it takes no energy to form. Okay, so let's go ahead now that I did that little sidetrack. This is a very special case. Let's go ahead and plug it into our overall enthalpy of reaction using enthalpy of formation values. So we have that the enthalpy of the reaction under standard state conditions equal to the sum of the products minus the sum of the reactants, enthalpy of formation. So my product, I'm going to write this in pink for product, is SO3. So I know that, okay, SO3's enthalpy of formation value is -396.0 kilojoules per mole. And I have, according to my balanced chemical reaction, a molar value or a molar ratio of 2 of those compounds are formed. So that means times 2 of that much energy is released in this reaction. So that's my product, okay? And then I know I subtract it from the sum of my reactant energy. So I know that my reactants, the first reactant I have is sulfur dioxide. So I'm told that sulfur dioxide has an energy of formation equal to -296.8 kilojoules per mole. And I used, according to my balanced chemical equation, I required 2 moles of that compound that is involved in my overall reaction. Okay. I'm also noticed that I have 1 mole of oxygen. So remember, it's enthalpy of the sum of the reactants. So I have another reactant compound. So I need to add that to my overall enthalpy of reactant portion, right? And what I see is I have 1 mole of O2, but I know that the enthalpy of formation for O2, a pure element such as O2, is 0. So that's what I plug in. And I get that this is my sum of enthalpy of products. And this is my sum of enthalpy of reactants. And following, multiplication, like math rules of order, when I add all of this up, I get that this equals, okay, in pink, negative 396 times 2, which is, what's the math? Negative 396 times, oh man, mental math. Okay, that should be 792, negative 792 kilojoules per mole for the products, the sum of the products, minus, okay, negative 296.8 times 2, which should be negative 296.2 should be, that's almost 600, but it's not, it's 593.6, negative 593.6 kilojoules per mole, okay, plus, well, 1 times 0 is 0 kilojoules per mole. And then I simplify that even further and I get an overall value of negative 792. Give me a second to pull out my phone calculator. 792 minus minus, so that turns it into a positive. Okay, 593.6. And I get an overall enthalpy value for the reaction that takes into consideration the individual compounds enthalpy of synthesis, essentially enthalpy of formation, as negative 198.4 kilojoules per mole. And that would be the overall enthalpy for the specific reaction given my specific compounds that contribute to product and reactant. It is just a much more detailed mathematical process than graph reading of enthalpy, but the same principles, products minus reactants. So go ahead and go to page 4 in your workbook and try out more of these problems. If you can do math, and as long as you can keep yourself in order of what's a product and what's a reactant, and you pay attention to the sign values, you'll be fine. And by the way, just to review, this is an overall exothermic reaction, okay? Because we have an overall negative sign value. So good job, you guys, and start studying for that quiz coming up. Bye. Ooh, just in time for the bell.